In this video, we're going to go over example number 1 for charging and discharging capacitors. So example number 1 says, the graph shows the variation of potential difference V with time t across a 220 microfarad capacitor discharging through a resistor. Our job is to calculate the resistance of the resistor itself. So I'm starting to think to myself, well, how does resistance play into the discharging equations? And I'm remembering a data booklet equation, V equals V naught e to the negative t over tau. You might be thinking, Miss Miller, there is no r in that equation. Well, that r is hidden. That r is actually hidden in this tau, this time constant. Our tau stands for r times c. So I'm going to plug that in and see where that gets me. Okay, so now we have an equation that involves V and T, which makes me happy because we're given a voltage and time graph. And we see that R value that we're trying to solve for, and we are given C. So in order to use this equation, I need to make some comparisons about voltage. So I'm going to come back up here to the graph. And the first thing that I want to notice is this maximum voltage, this 12 volts. That's what V naught stands for in this equation, the 12 volts. Now, I also need a comparison for some later time when the voltage has dropped because of the discharging. And, I don't know, I guess I'll choose this point right here. I like this point because it's pretty easy to read off of my graph, but honestly, you could choose any other point that you like too. This point, I'm seeing that when t is 25 seconds, that my V has dropped now to 4 volts. So I'm going to use these values in my equation. My V is going to be 4 volts, coming from an initial V of 12 volts, and it took 25 seconds to get there. I'll carry down that R that I'm trying to solve, but I'll also plug in my C value, the capacitance value. As a reminder, that was given in this problem, 220 microfarads. So that's 220 times 10 to the negative 6th. So I'm pretty happy with how this equation looks. I have one equation and one unknown, so it's definitely solvable. But this might be a little bit tricky to solve, so I want to show you all the way through. The first thing I'm going to do is divide both sides by 12. That gives me 1/3 on the left. Now I'm noticing that my R is kind of stuck in the exponent of this e to that hot mess. So the way that I'm going to handle that, to undo the e, I'm going to take the natural log on each side. And when you take the natural log of e, it will cancel out. This then becomes the natural log of 1/3 is equal to negative 25 over r times 220 times 10 to the negative 6th. From here, I'll bring that r up out of the denominator, multiplying it to both sides. This will give me in the same step, I'm also dividing both sides by natural log of 1/3. And at this moment, you might be thinking to yourself, I'm a little nervous because my resistance looks like it's about to turn out to be negative. See that negative in front of the negative 25? Well, don't worry. There's actually a negative hidden in here. The natural log of 1/3 could be written as the natural log of 3 to the negative 1st power, right? Negative 1st is just a way of expressing that fraction. And there's a rule in math that when you have the natural log of something to the power, you can actually bring that power out front. And so that becomes -1 times the natural log of 3. So now you can see that on the top and the bottom, you have negatives, so those should cancel out. When you type this into your calculator, you get an answer that looks something like this. That's pretty messy. So I'm going to round that to be about 100 kiloohms. And that's the R value that we were trying to solve for. So take a look at this process. I used my graph to determine the values of voltage at different times, knowing that the initial voltage was 12 volts, and then later on it had dropped to 4 volts after 25 seconds. Using that in my voltage equation and remembering that tau is R times C, I was able to solve for my resistance value.